behavior too. Let us review the stress strain pore pressure behavior of soils under various triaxial test conditions. You remember we said the sample, soil sample, is cylindrical of diameter 37.5 millimeters and height is 75 plus or minus 1 or 2 millimeters. You provide with a flexible membrane, put a top cap, and then this is the plunger which applies the axial load. The confining pressure is acting all over. So the sample is enclosed by membrane, cap and the pedestal, and at the bottom you have an outlet so that I have a wall. If I open the wall, the water can escape, and then I can measure the change in volume from the water coming out of the drainage line. If you close it and connect to a pore pressure device, we can measure the pore pressure. So the sample is sealed by the membrane, and I can apply through water a hydrostatic pressure which is acting on the sides and on the top also. The additional axial load is applied by means of this plunger, pushes it. So this is how we can control. The drainage is controlled by the wall. If open it, volume change can be measured, otherwise the pressure can be mobilized. So when you have constant sigma 3, the whole thing will try to compress if you are allowing drainage, and here you have constant 1. When you are applying here vertical stress, even if there is no water escaping, the cylinder can become larger in diameter because now I am applying load on the top, and so it will try to expand. So compression and radial expansion. So please remember, even in an undrained condition, the soil can have vertical deformation because the diameter is increasing and the height is decreasing. The common test, as we said, is hydrostatic pressure is increasing, which means Q is constant, and when you apply the deviatoric stress, the stress path is at an angle of 45 degrees. The first part is called the hydrostatic application. This is the deviatoric one. The three possible states are allowed drainage in both cases, you call drain test, allowed drainage, no drainage, consolidated undrained, no drainage in both cases, it's an undrained test. Now if you look at the behavior, the two extremes are a loose sand and a dense sand. A loose sand I'm plotting against the major principal strain epsilon 1, which is vertical, and we are looking at the shear stress or the deviatoric stress. A loose sand will behave with gradual increase of stress and an asymptotic final value. You may get ultimate stress at relatively large strain of maybe 10%, 12%, etc. If I have a dense sand, I'll find that the strength is mobilized at a small strain of 2 to 5%, and then if you keep on loading or continue to deform, the stress decreases, and finally at large strains you find both are about the same. They are reaching the critical state. So this is how the stress strain behavior of loose and dense sands look like. If I look at the volume change, and here is the initial volume, in case of loose sand it will decrease in volume, and maybe at some stage it may slightly vary, but predominantly it will be volume decrease. If you have a dense sand, as we explained in the class, the tendency is for its volume to increase because the grains start moving, rotating about each other on this one. So this is how it looks like in triaxial compression. This is our vertical strain, and you get the peak stress, and at point D is a residual one. And here is the volumetric increase. Volume is increasing here in case of dense sands. So this is a very simple illustration of what you can expect. And now you can see here, suppose I have a loose sand. The void ratio is 834, and the void ratio of a dense sand is 0.605, and both of them attain the final constant strength value, which we called as the critical ultimate stress. The peak can be different, but the ultimate value is the same. and this is how the volumetric strain. Initially it is compressing. So once it compresses and it has reached the critical void ratio, it will deform at constant volume. If the volume change is 0, it means it's deforming without changing in volume. Whereas here, you can see that the volume is continuously increasing. The most important thing I would like to see is when you have the peak strain, the slope of this curve is the steepest. So that is where the maximum amount of work is being done, and that is why you get a very large strength. So the strength of sands or soils is because of cohesion, friction, plus energy used to shear it. Suppose now you do a consolidated undrained test, which means you are first allowing it to consolidate and then do an undrained test. So when I now look at the deviatric stress in case of, say, normally consolidated soil, and these plots are for over consolidated soils. In the case of normally consolidated soil, the stress is increasing and reaching more or less a constant ultimate value. And look at the pore pressure. Please remember, we said it's an undrained test in the second phase, so I'm looking at consolidated undrained test. The pore pressure also increases, and once the failure state is being reached, you will get more or less constant value. And you can see here the peak stress is around 18, whereas the pore pressure is being around 15 kPa or pounds per square inch, and so it's getting very close to the value. If I look at now a over consolidated soil, plot the strain versus the deviatric stress, it's increasing. It may not even get a final peak value, because as you can see here, when I look at the pore pressure, initially it may be slight positive value, but the pore pressure is becoming negative. If the pore pressure is negative, total stress minus pore pressure, and pore pressure is negative, the effective stress is more, you may not get total failure, and so instead of a volume increase, because it's an undrained test, you get a negative pore pressure. So this is the difference between normally consolidated soil and over consolidated soil. Loose sands and dense sands, the same type of behavior you get. So here is the same similar plots from undrained test. The only thing here is that in case of normally consolidated, you may get an asymptotic value. Over consolidated, you may get a peak value, but you cannot get C and phi, because no matter how much you increase the confining pressure, the behavior of the soil is the same, because under increasing confining pressure, all the pore pressure is equal to the applied confining pressures, the effective stress doesn't change. So this is how the failure looks like from an undrained test. So pore pressure coefficient, as I said, can be estimated from this equation which was given by Skempton. Pore pressure is equal to parameter B, inside the brackets, the confining pressure delta sigma 3 plus parameter A times the deviatric stress. So if I want to know pore pressure due to confining pressure, it's equal to B times delta sigma 3. And B is equal to 1. We can derive easily because it's a function of C of the soil and compressibility of the water, which is very, very low. And so we normally find that beta B is equal to 1. Here I am looking at C of the soil or voids, C of the grains, and so you find that this is equal to 0 and this is the porosity, so beta is equal to 1. If beta is equal to 1, you will see that whatever may be the confining stress, the pore pressure is equal to that, which means the effective stress does not change. A is found out the pore pressure due to deviatric stress divided by deviatric stress and into B, because we have said that B into delta sigma 3 plus A into this term. So B times delta sigma 1 minus delta sigma 3, that's in the denominator, and this is the pore pressure due to deviatric stress. So that is how we try to determine A. And in order to make sure if the soil is saturated or not, you have to use this beta. If beta is not equal to 1, then soil is not saturated. We keep on increasing sigma 3 till you get beta is equal to 1, which means I increase sigma 3 by 10 kPa, measure pore pressure. If pore pressure measured is equal to the confining pressure, it is saturated. Otherwise, you increase the pore pressure to 20 and measure and repeat the process.